practice continues with radical operations, only they're getting meaner now. These numbers are big and there's more of them. But, same idea. Root 108, root 8, root 48, root 50, not a single match. So, at first glance, this looks hopeless. So what do we try? We're going to take all of our radicands and try to reduce them. We're going to try to pull out perfect squares wherever possible. So, 108, as we all learned on our grandmother's knee, is 36 times 3. And then we have root 8, which breaks up into 4 times 2. Relatively easy. 5 over 4. 48 is 16 times 3. They ask that one a lot. You probably will have that memorized before too long. And 50 is 25 times 2. When writing these, I try to put the one that has the nice square root out front. That way it ends up next to the coefficient that you're going to be combining it with. That's not a big deal, but if you think to do it, it makes all of this a little bit smoother. So now I'm going to go through and do the roots that I can. Negative 5 times, that's 6, makes negative 30. Root 3. 3 over 4 times 2 is 6 over 4, which reduces to 3 over 2. Root 2. Minus 5 over 4 times 16. This is, the square root of 16 is 4. 4 here cancels 4 here, so we're just left with negative 5. Root 3. And 5 from the square root times 1 over 2 makes 5 over 2. And then we have root 2. So, how are we doing? Well, they don't all match, first of all. Unfortunate, but it happens. What we have is 2 sets that match. We have these 2 terms which contain root 3, 2 other terms which contain root 2, so we'll handle them separately. It's just like if we had several terms that contained x and other terms that contained y. So if we gather up the root 3's, we have minus 30 root 3, and we have minus 5 root 3, grand total of minus 35 root 3. Then we have 3 over 2 plus 5 over 2 root 2. That's 8 over 2, which is just plain old 4 root 2. And that's the best we can do with this. We can't add these because they do not have the same radicand. We've already reduced them as far as we can, so we can't get any further with that tactic. So that's our finished answer. And now they give us a really horrible one with cube roots. Let's see. Can we do any of these, or can we factor any of these out? The cube root of 64 actually is just 4. I can do that one at a glance, because 4 times 4 is 16, times 4 is 64. Now, that probably won't be that lucky again. 375. 375 is 125 times 3. Remember to put cube roots on both pieces. And then 54 has a 27 in it. Root 27, cube root 2. If you're worried about where the 125 and the 27 are coming from, after I finish this question, I'll go back and talk about that a little bit more. So for now, hang in there. 24, I can take out an 8. Cube root 8, cube root 3, and it's all over 2. So what can we evaluate here? 4 over 8, I should reduce that. That's just 1/2. No reason to make it more complicated than it needs to be. So we have 2 times the cube root of 125 is 5. Cube root 3 minus 2 times the cube root of 27 is 3. Cube root 2 all over 3. And then we have 5 times the cube root of 8 is 2. Cube root 3 all over 2. So 1/2, 2 times 5 makes 10, cube root 3, minus 2 times 3 is 6, divided by 3 is 2, cube root 2, and then 5 times 2 is 10, divided by 2 is 5, cube root 3. So, what can we add here? This doesn't have a root in it at all, so we're pretty well stuck with the 1/2. Here's a term which contains the cube root of 3, and here's another one. So we had 10 cube root 3's, we lost 5 of them, we have 5 left. And finally we have this term containing the cube root of 2, which doesn't combine with anything else. So that would be our finished answer. That's as nice as we can make it. Now, if you're a little worried up here, you remember when we were doing square roots, the numbers we try to pull out of square roots are numbers like this: 4, 9, 16, 25, and so on. These numbers are called perfect squares because they're the square of a whole number. That means they have nice, obvious square roots. The square root of 4, it's got to be 2. The square root of 9 is 3. Square root of 16 is 4, etc. If we ask you for the square root of 64, you think, what times what makes 64? And you know what the answer is? It's 8. So when you're working with square roots, the numbers you're trying to pull out are these guys, the perfect squares. In this question, all of these are cube roots, and so we're looking for a different set of numbers now. We're looking for what are called the perfect cubes, and they are 2 cubed, which is 8, 3 cubed, which is 27, 4 cubed, which is 64, 5 cubed, which is 125. They don't generally go much higher than this, except every so often they'll whip out 10 cubed, which is 1,000, just to see if you can handle it. So if you're dealing with a cube root, don't try to pull these numbers out. It won't help you. You need to pull one of these numbers out. Quite often the 8 or the 27, occasionally one of these bigger ones.